And good morning to everyone, or afternoon or evening, depending on where you are in the world. I want to welcome you once again to our series on mangroves and their importance in climate change and other aspects of ecology. And you will recognize our speaker for today, who is Drude Lacerda, who is from the Federal University of Ceará in Brazil. Drude is the person who actually has organized the series for us, and I want to take this opportunity to thank him for all the work that he put into doing that. And of course, he also did the introductory series, the introductory seminar in this series. Just to remind you that Professor Lacerda is a full professor at the Federal University of Ceará in Brazil, and a senior researcher at the National Council for Scientific and Technological in Brazil. He's a member of the Brazilian Academy of Sciences and a fellow of the World Academy of Sciences and the Future Earth Coasts Academy. He has served as a visiting researcher at the University of Hamburg between 1986 and 91, and at the University of Toulon in France between 98 and 2006. He coordinates several national and international network programs on mangroves, including the Continent-Ocean Interface the Continent-Ocean Interface Network. And I'm pleased to announce that that network that Dr. Lacerda heads up has just signed an agreement with the IIES so that we can do further collaboration in the future. And so with that, I'd like to turn it over to you, Drude, and let you get started with your talk.
Yep. Thank you very much, Doug. It's my pleasure to be here again. I had the opportunity to give the first lecture of this seminar series, and then I will talk today on a more specific aspect of mangroves in the environment, which I particularly like because I worked with that for many years. I have put 4 references of review and synthesis works on the topic of this present presentation, except that Doug told me the first one didn't work, so I put it again down there in the chat, and it seems to be working, at least for me. I hope it works for you. So those 4 papers discuss many aspects of mangrove pollution, mitigation of pollution, effects, and things like that. So for a future reading is to follow this short talk. So I will first start by sharing my screen. Let's see if it works. Oh, you're not seeing it. Are you seeing that? No. So
yes, we can see that.
Sorry. Let me do it again. I just closed it. Yeah, do you see it?
Yes, we can see it, but I think you need to make it full screen.
Good, yeah. Well, now it's a full screen. So the topic of this lecture today is about how mangrove are facing a important environmental problem, which is derived from the fact that they occur in an area that directly competes with over 70% of humans. Most of the large cities, most of the large settlings of human society, even from very old times, occurred along the interface between the continent and the ocean, which is exactly where the mangroves thrive. So mangroves are facing problems derived from this high density occupation of human beings for many thousands of years. And I told you in the first lecture that it's very difficult to try to eventually know the original mangrove area in the world because exactly of that. Since prehistorical times, coastlines has been occupied and the competition between mangrove and humans very clear. You have two different types of drivers that impact through mangroves, mostly local drivers and distal drivers that can impact indirectly mangroves. The local drivers impacts directly by emitting pollutants, effluents, but also directly deforesting mangroves. In a very, very simple way, most of the most important drivers are aquaculture and urbanization in industry. Those two drivers are widespread worldwide, mostly aquaculture, probably today the most single driver of environmental impacts in mangroves all over the world. It's growing at an incredible rate of 10 to 20% a year, and there's no way of thinking this will decrease in the near future, mostly because most of the proteins today from fisheries come from aquaculture. Most of the structured fisheries are stabilized or even close to extinction of many economically important species. And presently in Canada, and always reminds of the port problems in the Great Banks. And this is happening everywhere. So aquaculture will probably increase its impacts on mangroves in the near future, either directly by cutting forests and substituting shrimp ponds, but also by emitting large amounts of nutrients and heavy metals. And this is a very interesting thing because very few people realize that shrimp culture is based on fish meals, and fish meals has a lot of metals in it, especially those that biomagnifies, like mercury, arsenic, and lead. And therefore, you concentrate this metal and give to the shrimp, and it ends up in ecdysis and feces and out into the environment. In fact, the emission factor of agriculture for mercury, for instance, is 10 times higher than from untreated sewage, for instance. Thanks that the area is still very short compared to urban areas, but it's today is probably the most important driver of impacts in mangroves. And the thing is, most of society react to these drivers, but most of them don't take an important concept that the world is changing. So most of the laws end up either not considering that the world is changing, so what they decided as limits may no longer be a limit any longer, such as concentration of substances, pollutants in water, for instance. And also, both urbanization and agriculture and industry, we're talking about strong capital bases. So normally what Professor Raquel talked the other lecture on the importance of community-based management, they normally cannot face the big capital. And then I have this experience in Northeast Brazil, where agriculture is probably one of the most important economic activity in many municipalities. Therefore, it's very difficult to really enforce environmental law, even when they exist. Well, urbanization and industry, they hardly convert mangroves because it's set on the outskirts of cities or harbor development. Most of this development is done inland, but they produce a lot of wastewaters and effluents that will eventually end up in the mangrove, resulting in contamination of the biota, eutrophication of estuaries, and siltation of estuary. Both those two activities generate a lot of sediments. Yeah. The thing is, these two activities, they don't follow ecological rules, they follow economic rules. So if you have an economic crisis, it's possible that people will be pushed on to mangroves to make poor houses. If you have a lot of money in your economy, probably industry will thrive, and then it means more effluents and wastewater. Therefore, it's also another driver which is very difficult to control only using the legislation on the environment. And it's all over the world. Most of the continental margins are occupied by huge cities and urban areas. One thing which is very interesting is that more recently, and we're going to have a seminar by Professor Alex at the end of the seminar specific on that, which is the increasing programs of replanting and restoring mangroves. There is a key date for that. This is December, 4th December 2004, when that huge tsunami, killed probably 500,000 people in Southeast Asia. And it was very interesting. By then, ISME has promoted a very nice seminar on how mangroves can protect shorelines from events like that. And it's very interesting because many papers have shown that the coastlines where mangroves were healthy and abundant were very well protected. I mean, the damage caused by that was very, very small compared to the other areas. And there's this, obviously, normally humankind reacts to disaster more promptly, and they did exactly that. So throughout the world, a lot of programming of replanting and restoration started. And this is very important because it actually protects coastlines from extreme events. And more recently, with the acknowledge of our society's incapacity of controlling fossil fuel combustion and emission of CO2, people realize that mangroves can also be a very important way of abatement of CO2 emission. Due to the extremely high productivity, the anoxic environment that we're going to see in this lecture, it can be a very good ally in mitigating the impact of carbon emission to the atmosphere. And this has been a very positive thing. It's becoming a huge initiative worldwide. There are some other drivers, as I said, which are not located close to the mangroves, but do affect mangroves a lot. And the most important of them are basically damming, which is normally built dams or diversion of rivers far from the coast, but they affect the sedimented salt balance of the whole lower basin of rivers. Eventually, they may cause erosion in the coast because of imbalance of sedimentation and erosion, mostly in a scenario of global warming where ocean forcing is increasing. And also, since they are very far from the coast, normally the watershed committees do not include coastal communities when they decide what to do with the water. So even when they are very well committed to a kind of ecological hydrology that thinks about maintaining the ecology of the river, they don't think about the coast, which is sometimes 200 to 300 kilometers downstream. So normally people that depends on mangroves are not included in those committees. So the response from the society is not what we would like to have. Damming, it was stabilized for many years till most regions of the world annual rainfall start decreasing, like in northeast Brazil, for instance, but in other areas. And this triggered a new generation of dam construction. So probably this driver will be increasing the next maybe decades because of global warming and decreasing rainfall, and obviously following the necessities of an increasing population and other human activities. And then the other one is agriculture and husbandry, which is also increasing worldwide, and mostly commodity agriculture, commodity beef. Normal family agriculture doesn't cause this kind of problem, but this large-scale agriculture produces a lot of effluents containing huge amounts of nutrients. And well, the extreme example of the huge anoxic zone in the oceans, which is basically due to nutrients coming from large-scale agriculture. So eutrophication and contamination of the biota can come out from these effluents. I talk about contamination because most of Fertilizers today, they have a certain amount of trace substances, among them pollutants. So they eventually contaminate the surrounding biota because the estuary is where everything accumulates. And siltation because both activities resulting in large mobilization of sediments. Again, most of this is done very far from the coast. So the same problem with damming. Normally, the people organized to deal with this large-scale agriculture and husbandry are not acknowledging mangroves at all. Eventually, it's probably stabilized, but it depends a lot on the standard of living of the human population and its increase. I mean, if both increases, we need more food, so we need more areas, and And the last one is climate change, which is a global phenomenon and affects directly mangroves, both by changing hydrodynamics, therefore sediment erosion balances, frequency of extreme events, like I mentioned, tsunamis and storms and other tidal bores, and a very important thing, which is its capacity of mobilizing pollutants. We're going to see this in detail because in the case of mangrove, this is a very, very key step in understanding the effects and, on the other hand, how to mitigate this kind of contamination. So the impacts are mostly erosion of coastal forests, soil, pore water salinity increasing, and this has a very important impact on mangrove because they react to this by migrating where the salinity keeps the freshwater plants out. There's no specific response for the society for this, fortunately. Even the more clear one, like CO2 emissions, you know, humanity is absolutely not able to cope with that. I mean, the emissions are increasing, even if we know the impacts of that. So probably this will be increasing for the next decades easily. You can see I put these dates 1994 and 2024 because 1995 is when people start making the association between fossil fuel burning, CO2 emission, and global warming. And then this triggered the Rio Conference and many other conferences and COPs and everything in the past 40 years, and CO2 in the atmosphere just remain increasing and increasing more fast. And today, well, probably this 420 ppm is already past. I don't know, I have to check the killing curve, but it's probably more than that today. So, one thing important is all these drivers being close to mangroves or far from mangroves, they release nutrients and pollutants, all of them, in different scales. Or, like global change, they don't emit pollutants except for CO2, but they have a very strong potential to remobilize deposited pollutants. Well, as I said, estuaries, where the mangroves exist, are typical accumulation environments. So most of the pollutants produced in the continent are being accumulated in estuaries. And this is a process lasting thousands of years. You know, if you take a core sampling in an old estuary, you can easily see the impact of prehistoric emissions of trace elements, for instance, in this core segment. So estuaries are classically an accumulator structure in nature. So if you want to cope with that, if you want to understand the impact of mangroves and how the mangrove can eventually be used to mitigate the effects of this pollution, you have to know a little bit more what mangroves are. And most of all, a very theoretical concept on till when mangroves will be healthy. And then I got to this next slide, which is a theoretical framework I've been discussing a lot with colleagues, including Doug, about tipping points in nature. And this is a classical example. I mean, instead of showing the graphs to most of you, I just give you an analogy. if you take a kitchen sponge and brand new, just open it and put into tap water very slowly. There's nothing coming down the sponge. I mean, everything is being absorbed to the sponge, and then suddenly, in a tipping point, all the water coming in start leaking down. So in nature, ecosystems and mangroves in particular act exactly that. If you go to this curve, what you see here on the basis is a concentration of a given pollutant mobilized by any means, either by effluents or other. And the amount of pollutants immobilized in the mangroves in the y-axis. And you see the difference between the load that is being put into the mangrove and the concentration mobilized. When you are starting this, that I call capacity, support capacity curve of a mangrove, you see you have very small increase in the load of pollutants in Y and very small mobilization of pollutants to the environment. But when you go up, this is not a straight line. So the same amount of a pollutant that we put here in key 1, you put in key 2, but then it encounters the mangrove in another completely different environmental situation. So a huge amount of pollutant is being mobilized. And I can give you an example that will make easily understood. This is a balance of phosphorus, a very common pollutant from effluents of both agriculture, urban areas, and everything like that. And this is a comparison between two mangrove forests. One that is submitted to effluents from about 2,000 hectares of shrimp ponds that you see here on your left. And on the right, another forest, but receiving effluents from only 9 hectares of ponds. Obviously, the first clear thing is the huge amount of phosphorus from this left side forest compared to the right side forest. But then the most important thing is not the amount of phosphorus coming in, but how much of this phosphorus can be incorporated into the mangrove itself. Because many people know that mangrove can be used to mitigate emission of organics, because it can be deposited there. Most of the particulate, you can see the architecture of the roots. They are fantastic for filtering particles, for instance, carry nutrients and metals. But when you compare the two forests, the one receiving influence from these 2,000 hectares of ponds, it's able to cope with only 46% of the load, meaning only 46% of the phosphorus is eventually accumulated in sediments or uptake to form new biomass. While the other side, you see the mangrove forest that receives effluent from only 9 hectares of ponds. It can accumulate up to 96% of this load, both in soils or becoming new biomass. So, meaning, coming back to that curve, the right-wing forest receiving small amounts of pollutants is here. Mobilization is minimal. It's only 4% of what this load entering the system. But then you go to the right one that receives 2,000 hectares of shrimp ponds. The same amount of phosphorus results in over 54% releasing. So somewhere between here, it's a tipping point where mangroves will be unable to cope with excess nutrients. The problem is we don't know where we are in this curve. And this is a huge problem. And probably you have mangroves close to the key 1 and a lot of mangroves close to key 2 and many others in between. And obviously, any mitigation measure, any legislation, any new creation of drivers of pollutants has to take this into consideration. And if you see that some of those mangroves, a lot of them, are already degraded or even converted, then if you look at the beginning of the y-axis, you can see that they already cause a large mobilization of pollutants. So they lose their capacity of accumulating and mitigating the emission of such pollutants. Well, so this is depends basically on the biology of the plants, and we're going to see later how the physiology and anatomy of those plants may affect this capacity. The other important concept of the mangrove environment, people don't normally think about that because we always with our noses in the air. But if you think quietly, you see that mangrove is a completely crazy environment. Thinking about a planet full of oxygen. I mean, mangrove thrives in a reduced environment, in an environment where there's no oxygen. It's amazing because it's one of the few ecosystems on Earth that thrives in an anoxic environment. Yeah, there are some small examples, salt marshes, but only half of the year. But mangroves year-round are submitted to a reducing environment in the sediment, meaning there's no oxygen. Wow, that's a problem because if there's no oxygen, how bacteria will survive? So most of the bacteria in mangrove, they take out the oxygen in sulfate, in seawater sulfate, it's very abundant, and do a dissimilatory breaking down of the sulfate. Dissimilatory because the bacteria is not interested in the sulfate, but on the oxygen, to oxidize organic matter, mangrove organic matter. And then there are two problems in that. First, this is a very inefficient metabolism compared to our oxic respiration. I mean, respiring organic matter using oxygen from sulfide is a very tough task for the bacteria. It has to spend a lot of the energy that produce to break down the sulfate. So only a small amount is actually used for oxidizing the organic matter. And as then you probably by now know from the two first seminars, that organic matter from mangrove is a very hard material. I mean, because of many adaptations to live in a UV-rich environment, hypersaline environment, water-lodged environment, the physiological and anatomical adaptations to cope with this environment results in organic matter which is very refractory. So, because of this inefficiency of this metabolism and the refractory nature of the organic matter, sulfate reduction produces some very important byproducts that will be very key to mitigate some of the pollutants we've been talking about, but also make them more bioavailable depending on the situation. For the phosphorus, for instance, this situation results in the position of iron phosphate. But again, when it goes to the reduced environment, it may release more phosphorus. Probably the example that I showed before was an extra reducing environment due to eutrophication of the mangrove environment by that huge shrimp farming effluent. And the other one from the sulfate reduction is acidity. So pH in pore waters decrease, and pyrite, iron sulfate. But pyrite is a tricky thing because it's not only iron. We're going to show later. I mean, this precipitation can co-precipitate any chalcophilic element, not only iron, but it's mostly iron because iron is not most abundant. And since it cannot oxidize organic matter to CO2 and water, there is a huge producer of dissolved organic carbon. And this dissolved organic carbon can mobilize some pollutants, as we're going to see. Well, iron sulfide precipitates and stays in the sediments whenever the sediment is still anoxic. So this beautiful rhomboid structure that you see in these pictures. They are pyrites formed by sulfate reduction bacteria. What is the major difference between a pyrite that probably one of you that is listening to this are using as a jewelry, either in a necklace or earring or anything? Pyrite is beautiful. But the pyrite you use in your jewelry, they will form geologically, so they are very well crystalline, so you can use it without oxidizing. Sometimes you have to clean it because it eventually oxidizes a bit. But this, from border pyrite, is a biological substance. While the geological pyrite takes millions of years to be formed, here it can be formed in 24 hours. But it's not a well crystalline structure. So they can be easily oxidized if oxygen migrates into the sediment. And the other important thing is that those pyrites are not only iron sulfide. You can see from this micrograph, the electron micrograph, that other sulfophilic metals can co-precipitate. And in the left part of the slide, you can see what would happen to a trace metal. For instance, cadmium, a very toxic pollutant, or lead arriving into a mangrove. They normally will arrive in a mangrove associated with particles, both from the sea or from the continent. The dissolved fraction is negligible because they are not soluble in water. So you have traces, part per billion of those metals dissolved in water. Most is associated with particles. Now, the first process is a simple physical deposition of this particle because of the roots. As I show you in the two pictures of the phosphor case, the architecture of the roots decrease the force of carrying capacity of particles to the waters, and everything precipitates easily. Stokes' law, even very fine clay particles deposit in the mangrove because of this decreasing hydrodynamics. But then this, for the particle, it means moving from an anoxic environment in the water to an anoxic environment in the sediment-water interface. And then what happens is, first, all the stable elements in oxic environments are reduced and eventually mobilized, like iron and manganese, for instance. And they release the metals that co-precipitate with iron oxide and manganese oxides. What they found acidity, as I showed you in the previous slides. So it's, well, they are very capable of becoming and staying soluble in pore waters, but also they found sulfide and GOC. So, and then will depend on the affinity of each pollutant with those substances. Most chalcophilic elements will very, very rapidly be precipitated or co-precipitated in those beautiful flamboyant pyrites, as you can see in the picture here. And some that has a very strong affinity for organic matter, like mercury, for instance, will probably remain in solution in the pore waters, associated forming organic complex. And this may be exported from the mangroves. And you're going to see that this may become a very important thing in a global warming scenario. This is a close-up of those beautiful pyrites. I say beautiful because I love them, but you know, they have a different opinion. Doesn't matter. But those flamboyant pyrites, as I said, they can easily precipitate by the action of the sulfate reduction bacteria producing sulfides, and then the amount of iron dissolved when they pass from the oxidized to the reducing environment precipitate pyrites. But then when you look on your right wing of this picture, you see that it's not only iron. I mean, iron can be up to 90% of these sulfides, depending on the amount of the other substances. But you still have sulfur, iron, but you can have also sulfophilic elements. In this case, in this pyrite, 7% of it was copper, for example. Yeah, and in the example before, there was zinc, mercury, and any other sulfophilic element. It depends on the relative concentration of it. So this mechanism immobilizes trace metals. Most shocophilic metals are important environmental contaminants. So maybe we could use that for coping with pollution. We're going to see some examples soon. The other adaptation that can be used to mitigate those things is the defenses the mangrove produce to cope with salinity and lack of oxygen and on and on and on. I mean, this harsh environment that mangroves thrive. And one important thing, again, is their ability to pump oxygen from the roots into the sediments. And they create this beautiful oxidized layers where iron easily precipitates. You can see this blue color in these pictures is basically iron-free precipitation. And again, similar to the pyrite in the sediments, iron oxide also co-precipitates metals. So not only iron is immobilized in the rhizosphere, but also any other trace elements. And this is a very important thing because this protects mangroves not only from sulfides by pumping oxygen, but mostly protection from trace elements, including iron, because it can be very high concentration. They stay in the rhizosphere, deposited as iron oxides containing pollutants. And this may reach very high concentrations, but it's not absorbed by the plant. So the plant is protected by this iron plate. And this is a kind of iron shield to the plants. And some of mangrove plants, like the Avicennia, can also, through salt glands, excrete salts. And as you can see in this micrograph, it also excretes iron through salt glands. And again, this iron is iron-free precipitated metal, so it can also excrete some toxic metals through salty excreting glands, protecting the plant from the effects of toxic concentration of trace elements. And how can you use this mechanism, these natural properties of mangroves in our benefit? This is an example. This is Guanabara Bay in Rio de Janeiro. It has, for many years, probably one of the largest in South America, at least, solid waste disposal site that received about 14,000 tons of solid waste per day. I mean, the basin area harbors about 30 million inhabitants, apart from Rio de Janeiro city and many other suburban areas, very large. And it was deactivated by the year 2000, something like that. And then you have a huge problem. You have a huge deposit of solid waste leaking many different substances, pollutants, everything that you can imagine do exist in a landfill. So the first pictures up is the landfill as the date it was decommissioned. You see some trucks moving material. And then we proposed to the government, to the local government, to replant mangroves surrounding this landfill. You see, in the second picture, the mangroves already growing, and in the third picture, the old tailing area, or not tailing, but the residual landfill, completely surrounded mangrove. Those mangroves were replanted. Well, maybe 100 years ago, they were natural, but then they were destroyed, that you can see in the first picture, and then we put them again. What happened there? You see those graphs behind, exactly what I showed before. At the root level, where you have the position of sulfide, you have the rhizosphere of mangrove mostly, you have a very high concentration of trace metals. You see the root mass in the first graph and the accumulation of mercury and zinc. And this is exactly the result of the mangrove roots pumping oxygen and depositing iron oxides that precipitates all trace metals around. Just in a parenthesis, iron oxides are the major transporter of trace elements, trace metals throughout the tropics. So here it's the same thing. So what you see is that you create a very high concentration level of metals at the root level. And then it decreases sharply to the surface. Yeah, you can see in the black dots where there's no roots, areas that are still growing the mangrove. Then you can see a typical line of metals being exported to the surface, and then eventually to pour water, surface water, end up in Guanabara Bay and the fisheries and on and on and on. So when you put the mangroves, it can block this mechanism of base metal transfer to adjacent coastal waters. And then it's immobilized there. So below this beautiful mangrove forest, there is a huge horizon of about from 20 to 40 centimeters deep in the sediments, incredibly rich in trace elements, but absolutely immobilized. It cannot be uptaken by the plants. It cannot be transferred to the coastal water. So we didn't took out the pollutant from the environment, but we solved the pollution problem. And this is a very important aspect. You can use that also in effluent from a smelting plant. This is a smelting plant in another bay, in Sepetiba Bay, where we also start planting mangroves along the channel that usually bring effluents to the bay. And again, you see the same curve. This time is specifically extracting copper from iron plates in the roots and the residual. And you can see again a huge concentration of copper in the rhizosphere of mangroves. Again, not getting rid of the pollutant, but immobilizing it. So getting rid of the pollution, not the pollutant. The problem is that we are facing those local drivers that most of them produces also erosion. Global warming that produces erosion throughout the coastlines of the world, mostly where annual rainfall is decreasing, like in semi-arid environments. And then what you do, you go and you see that there's in northeast Brazil, a typical behavior of a coastline from the 90s onwards. You see in September 96, this is the decrease of the coastline in terms of loss volume of sediments, 46% in 6 years only. So it's huge, this erosion problem in semi-arid coasts. And then you can see that what happened? You expose that reduced environment to oxygen. First thing, well, most important thing is that then you shift from a very inefficient sulfate reduction metabolism to a very efficient oxygen oxidation. And then the first thing, you oxidize most of the deposits of organic matter and release huge amount of CO2. That's a very important problem nowadays. And maybe Professor Alex in the replanting seminar will talk again on that. Because while mangroves can be a very good ally of humankind as a sink of CO2, if you cut them out and expose this carbon to oxygen, you very, very fast release of CO2, both to pore water, to the atmosphere. And I may post a paper that people from our group just measure this emission, and it's huge, and can just very fast release to the atmosphere all the carbon that's been accumulated in those sediments for maybe thousands of years. So this is a very important thing. Obviously, this consumes oxygen from the water column. So you're going to create anoxic conditions in the water column, not in the sediment. And then it's a problem for the organisms, yeah, for the fish and crabs and everyone there. While down in the sediments, it doesn't cause any problem. One other important thing is that mangroves normally sport a lot of alkalinity. And in a way, it can help in another mitigation procedure. And it exports even when it's working finely. You don't need erosion to export alkalinity to coastal waters. We're going to see this later. And then what happened in this profile? Here is the distribution of organic matter, density, and mercury in exactly that same segment. This is a 4 where you can easily see the impact of the roots. The density decreases. This is the hydrosphere. Organic matter increases in the hydrosphere, and mercury increases in the hydrosphere. So it's perfect. That is exactly what we showed in the Guanabara Bay example. But then you erode that. And then if you do that, you take exactly the layer of sediments that accumulates the most amount of pollutants. Meaning that if someone decided to cut the mangroves around the Gramacho landfill in Guanabara Bay that I showed, you're simply going to release an enormous amount of trace elements that is being actively accumulated there by this process of sulfate reduction, oxygen release from the roots. So it's a very efficient, as you can see in this picture, way of storing trace metals in a very low bioavailable condition. But once you break this, you're going to release a huge amount of trace elements. And this, unfortunately, is what's happening due to global change. I mean, global warming is increasing, ocean forcing. This is an example in Brazil. I mean, the South Atlantic is the ocean that accumulates more heat among all oceans. So ocean forcing is increasing. And then you see the effect of erosion in the fringe margins. But also, you increase mangroves because they do migrate in the interior, because this ocean forcing, while eroding the coastal forests, impede sediments going into the sea. So it accumulates and it migrates. So all this process, in fact, will start migrating inland. And you say, well, then it's all right, because you're destroying the coast and you're creating the inland, and then, well, everything will be even. Except that the velocity of the process are different. What we're going to erode in the fringe margins are metals deposited for thousands of years, while the accumulation capacity of these new mangroves, although high, will accumulate the metals present in the environment today. So it will take 1,000 years again to get all that amount of trace element that was eroded at the fringe forest. And this is the same thing for carbon. Yeah. So in fact, it's not an evil balance. It will be an even balance if you think about thousands of years. Then it's okay. But in this rate, no one will be here in 1,000 years, so it doesn't matter. And there's, as I said, the other important thing of mangrove that can be used to mitigate a huge problem nowadays in the oceans, which ocean acidification. It's quite crazy. It's a very good example on that first table, that our inability to cope with these things. People know that the ocean is being acidified because any college student can make the simple chemical reaction and say, well, if I increase the CO2, I will increase acidity when it dissociates. I mean, any college student does that. So we know that for 100 years, not 100 years at least. But the problem of ocean acidification became a topic of the IPCC, which is only good people working there, very excellent scientists, just a few years ago. If you take the first IPCC report, there's nothing about acidification. And nowadays, you know that most oceans are being acidified, certain oceans more than the other. And then mangroves, again, can be a very good ally to cope with that, because they export a lot of alkalinity. And this alkalinity can eventually counterbalance acidification, at least in the coastal areas. And this is a very important mechanism that can be used in the future to mitigate these other problems. Well, I'm sorry if I was a little bit too fast. I mean, the topic's a little bit more complicated than I thought. I should have thought of a more soft thing. But anyhow, as I said, I have posted 4 references in the shop for everyone. Those references are synthesis work and review works on pollutant and trace metal impacts on mangroves. Mostly, obviously, has a basis for Latin America because it's where we work, but it applies for many other regions of the world. So just to settle down a little bit on the knowledge, you can go and read these publications. So again, I have to thank the EAS for this opportunity and the other supporting agencies and groups that make this seminar possible. So I'll be available for question now. Up to you, Doug. I'll pass the
Yes, thank you
stage for
very
you.
much, Drude, for that excellent introduction to the geochemistry of mangroves and taking us into some depth around those the mechanisms that control some of the geochemistry. So now I would invite the audience to ask questions. You can do that either in the chat if you prefer, or please feel free to open your microphone or your microphone and your camera if you wish, and ask any questions. Do we have questions for Drude?
Yeah, as I said, it's a little bit a dry subject anyhow.
No, that's okay. Sorry, Raquel, did you?
Yeah, there's a question in the Q&A if you want to check there.
Let me open the chat here.
Oh, in the Q&A, I'm sorry. Okay. No, I do not see anything there.
I can read it if you want.
Yeah,
in the chat?
Go ahead, Raquel, because it doesn't show in my Q&A.
Yep, it says, how can we estimate the carbon losses from the mangrove and other land use where mangrove was in the past?
Yeah, that's a very good question, because this is a discussion I was having with colleagues some days ago. Well, the first way to estimate that, I mean, those chemical reactions are known. So if you know the amount of carbon that is in there, in the sediments, you can estimate with very good precision the amount of CO2 being released by a certain metabolism. For instance, if you pump oxygen in a sediment with that amount of organic matter. So since the equation is easy, you can do that. But then the problem is that you have to know how much carbon is in there. And this is a problem. If you look at the literature, any one of you can do that and consult the latest data on mangrove carbon in sediments. You see, they are absolutely crazy. I mean, people make some generalization based on half a dozen cores done in different areas in the world and extrapolate it from a global basis. For example, if you take only Northeast Brazil, you can vary by about 2 orders of magnitude the amount of carbon in mangrove sediments, only in the small stretch of coast from Fortaleza to Natal, for instance. So you can imagine globally. So most of those estimates you have to take very care. To measure how much CO2 will be released, that is the easiest way, because the equations are simple and you can mimic it in the laboratory, pumping oxygen in an anoxic environment and measuring the release of CO2, or even measuring CO2 directly at the sediment water or sediment atmosphere interface. That is not trivial, because the equipment that you need is not so trivial, but it's easy. I mean, it's a calculation which is easy to be done. The problem is to know how much carbon is in there. And then, in the second part of the question, if, at least in my view, we don't know with at least a 50% variability the amount of carbon that is already actually in the mangrove sediments today, to think about doing it in the past is even more difficult. You would be much better coring. There are major areas that were mangroves and nowadays are, like in the northeast coast of Brazil, there are a lot of mangrove sediments below sun dunes nowadays, and they have a lot of carbon and was formed maybe 1,000 years before. Below the Australian barrier reef, for instance, colleagues from Australia had found out huge layers of old mangrove sediments full of carbon also. So that is very difficult. But once we know this number, then how much will go into the atmosphere is easy. There are some field experiments, unfortunately, I think, because they are real, where shrimp farming cut down mangroves to build towns. And then you can measure the amount of CO2 going into the air or into the water because of that. So those are the way to do that. But the key thing, and this is in fact became a global exercise.
Well, I think we have
10 centimeter core and 1 meter.
Sorry, Drude, we kind of lost you there for a second. Can you just repeat the last couple of sentences of your answer?
Oh yeah. Sorry, I don't know what happened. No, the thing is, there is a group of international scientists that is trying to organize this field of knowledge, because it's really a mess. I mean, people compare sediment cores 1 meter deep to 50 centimeter deep to 10 centimeter deep to 2 meter deep. And obviously, the amount of carbon is different. They compare carbon under Rhizophora with carbon under Avicennia, which is also different, not only in quality, but in quantity. So we need a lot of more protocols to have comparable data that I can, well, make a table of carbon content in the soils of Indonesia comparable to Brazilian soils and on and on and on. Nowadays, I think it's a very important effort that people are doing, because it's a kind of alerting the society for the potential problem of releasing huge amounts of carbon deposited. And this is probably the same thing as we're seeing now in the permafrost, something very similar. So we have to raise conscience about that in the public, but we need a lot more of experimentation to actually have good numbers. In my view, at least, I don't think we have these good numbers.
Thank you, Drude. Drude, can you share your email ID for further communication?
Oh yeah, sure. I think it's available in the ES file. I don't know, but I can make it right now easily. Let me put on the chat. I will post it for everyone. Yeah. Well, that's it. So everyone has my email. You can share the. So.
Do we have any other questions for Drude? Maybe while people are thinking about that, just to follow up on the last question, the few times that I've been in mangrove forest areas, the thought of trying to get representative samples seems to me quite complex, given the structure of them. And I'm just wondering about sort of even within a single area, spatial variability and how you come to grips with that when you're sampling.
Yeah, you're right. You see, you saw the picture, so it's not an easy place to sample. And then the field works that has done that. For instance, there is a very comprehensive work done in a mangrove in southeast Brazil, in Bahia, which is very nice. They took a lot of coring, not only longitudinal to the mangrove, I mean, going from the sea inland, but also, and this is very important, from the edge of the water inland, transversally to the mangrove. And that's really amazing, because most of the time, this transversal transect shows much more variability than the sea land transect. But again, this didn't repeat in another mangrove. Another group did exactly the same thing, but couldn't found any significant difference transversally, but found incredible high difference from the sea to inlet, meaning that it's very site specific. So we need a lot of coring, a lot of work to actually arrive in a single number that would represent the amount of mangrove carbon in mangroves. Probably it will have to do at least in a regional level. I mean, you could say, well, carbon in mangrove soils from the South America, semi-arid environments, equatorial humid, tropical humid, semi-temperate, will probably have these classifications. And also, mangrove forests, they are very simple when you talk about species. I mean, there are very few species. Any tropical forest, 1 meter of tropical forest has more tree species than the whole mangroves in Brazil, for instance. But even so, they are very different in structure. The same species, Avicennia, can be completely different from one place to the other because of high salinity, lower salinity, water deficit, and things like that. And there's impact on the biomass, and there's impact on the carbon transfer through lithophore. And again, we need a lot of information. I'm presently writing with some colleagues here a review of mangroves from the semi-arid of Brazil. And then I try to compare semi-arid mangroves with northeastern mangroves. Well, there are 2 papers in northeastern mangrove and known in terms of lithophore, which is something that anyone can do. You can go with a basket and live there in the forest, and there's only 2 papers in the whole Amazon and only one known in the southeast. And these I couldn't find, 2 last week, and I looked a lot. So we need much more information on that. When you compare, for instance, people say about tropical soils in Brazil, for instance, maybe you have a grid of every 2 or 3 kilometers of soil samples throughout the country, meaning that you have millions of data related to carbon content in the soils, and probably in Canada is the same. But in mangroves, if you do that, maybe you can have 1,000 globally data. So it's quite crazy. I think we still need a lot of work to have 2 good sound global numbers.
Okay, so any final questions for our speaker?
There's one more in the Q&A.
Oh,
It
okay.
says, do you think looking at CO2 at the sediment water interface in water bodies or lakes in general is understudied? And could general studies like this help inform what is happening in mangrove ecosystems?
No, yes, because as I said, I mean, the reaction that controls CO2 fluxes from the ocean to the atmosphere are exactly the same as in the mangrove. What are the difference? I mean, you can put in a CO2 analyzer in a ship and cross the ocean making analysis, and the data will be very good because salinity nearly doesn't change, temperature nearly doesn't change. Maybe the wind intensity will change and will affect the calculations. But then you go to a mangrove, then, you know, temperature in a tidal cycle can vary depending on where you are. If you are in Southeast Brazil, it can vary by 10 degrees. If you are in Northeast, 2 degrees. Salinity can vary in a tidal cycle only between 0 to 40 parts per thousand, which is nothing like that. So that's a crazy thing. I mean, it's so crazy that most of the work that's being developed, developing equipment for this kind of measurements, they're made for the sea or large lakes, so they don't consider this change. Normally, those equipments cannot work in such a very environment. So only recently they are becoming some nice works on mangroves, because the variability of the parameters that control the equations of CO2 emissions vary too much. I mean, tidally, because you have the tides changing everything, but also from the coast to the sea, and annually, seasonally, because it depends on the continental flux, meaning that you have a good number, you have to do a lot of monitoring. In the case of CO2, things are becoming easier because some equipment being developed nowadays can work in real time, being deployed there and collecting the information for long periods. You used to have that in the ocean, but as I said, in the ocean is easier because nothing changed. In the mangrove, those equipments are still under development because they have to cope, they have to work finally in different environmental setting, mostly salinity, alkalinity, temperature, and winds. Winds here will be the less influence in the ocean, but the other variables of the CO2 transfer equation will be very variable. So you still need some technological development to really cope with that, like we do nowadays in the ocean, where you have billions of data taken from opportunity ships, for instance, and things like that. You cannot do that in mangroves yet, not in any estuary, in fact. But you need that. If you don't have this variability, then I can post maybe if I found it, it will take some time. But if I found it, I can pass on. There is a video of one of those expeditions we did in one of the largest mangroves in the Northeast, where we went there exactly to measure CO2 fluxes. There are some papers also that I can try to send through email. If you ask me and remind me, I can send all this to you. And in the INCT, the project, which is in the last slide that I show. Let me show you again. If you see it, I don't know if you're seeing it, but there are the emails
We can
of
see it.
there are the emails of the INCT, which is this global yin and yang. I mean, it's proposed the continent ocean yin and yang, and there is an email site address there that you can download these publications. I mean, the CO2 and the trace elements and everything. So you can just take it.
And I would remind people that these talks are posted on our website and our YouTube channel. So you can go back and pull up the slides and get the exact links that Drude has just indicated. So I think given our time, I will call a halt to the questions. But I just want to thank you again, Drude, for this very excellent talk. And I just want to remind people that we will have another talk next week, and our speaker will be Dr. William Vasquez from Fairfield University in the United States. And he will be talking on valuation of ecosystem services within mangrove systems. So I would invite you all to join us again next week at the same time. So thank you all for joining us today. Bye for now.
Bye-bye then. Thank you very much. See you.
Bye.